Alright, let's quickly go. Let's get this done. So we're going for our spectra. Hope that nothing's wrong here. This music is a bit loud for you guys, I presume. Oh yeah. Wait. Okay, you were hearing it twice, I think. Wait, no, you weren't. I'm decreasing my own mic volume. Incredible. Okay, I don't really care. Okay, anyways. So, first, if you want to talk about mass spectrometry, let's have a little background first. So, how is how is the spectrum even produced in the first place? Of course, if it's a spectrum, that means something needs to fall on top of a screen, and results are produced in form of a graph. So, visible light is infrared, as you already know, is part of the electromagnetic spectrum. That is going to be, it has its own range of light. Infrared is, it's on the left of the visible light. So it's going to have a continuous range of frequencies, infrared radiation. So, but our eyes can't detect them because the frequency is too high. So, too low. Now, if you shine a ray of so multiple, frequencies of infrared one at a time through a sample in an organic compound, you find that some frequency gets absorbed by the compound, or rather some frequencies get absorbed better, whatever. So if you had a compound and we have a range of frequencies in the spectrum, so we have from low to highest, and we shoot them all, we'll see that one gets absorbed and the rest kind of just pass through. So that tells us that a detector. So if you put on a detector or a screen on the other side, it'll tell us which rays pass through the compound with almost no loss, and which rays get strongly absorbed. How much it gets absorbed, how much that frequency gets. Yes, I still have time. Yes. 8:55. Gets through the how much particular frequency. So how much that frequency gets through the compound, or how much it doesn't, can tell you the percentage transmittance. Now the percentage transmittance out of 100, of course, because it's 100%, would mean that so if you had 100%, that would mean that all of it passes through, and none of it gets absorbed. So if you have one, and we have the thing that shoots out. Now in this frequency 1, suppose it's a 100% percentage transmittance. So the entire thing gets transmitted through. If you studied physics, that one video that we did, transmittance means that the fact that it goes entirely through without any absorption, right? Or rather, it gets absorbed and passes through, or something like that. I don't remember either. So it passes straight through without any absorption. In practice, that never happens, blah, blah, blah. Usually it's 95%. That's the highest you can get. Transmittance of 5%, let's say we have this and we have F2 and then we shoot through. Well, actually, not that much goes. Most of it stays in here, and about 5% actually goes past, gets transmitted through. That means, what this actually means, this tells you some important things about the bonds of the compound. So the fact that this one has a higher, and this one has the higher amount getting absorbed, and this one has a lower, or this one has a higher amount getting transmitted, and this has a lower, tells you something. And what does it tell you? It tells you about the compound itself, about the bonds within that compound. I think that's all we can do for now. Infrared spectrum, this is what it usually looks like. You're going to have a range. Notice how the thing goes from 1000 to 500, 500, 500. This is going to be a wave number. Wave number is just pretty much how many waves you'll have, how many wave cycles you'll have in a certain amount of length. Right here, how many wavelengths or wave cycles that you'll have in 1 centimeter. Okay, so you'll have one distance, that's going to be your distance that you set, and how many wavelengths you'll have in that 1 centimeter. That's going to be your wave number. So the higher number of wave number means that the higher number of waves within that one area, which means that there's a higher frequency. So if the wave number, as we can see, is increasing to the left, that means the frequency is increasing to the left. That means you can see the transmittance is changing randomly. There's no trend here. It's going really randomly. And of course, this is of a specific compound of propane 1 alcohol, 3 carbons. So yeah, that's going to be a wave, and it's a weird range of frequency. You measure a frequency. It's called wave number, but whatever, right? We shouldn't worry about too much about these change of scale halfway across, mainly because we see that infrared spectrum is consistent all the way through. We will see infrared spectras which are consistent. We will see some which change around 2000, and occasionally some that changes again around 1000. So as in, it's 1 changes until 2000, changes at 1000. Okay, kind of like that. You will see when we look at how the infrared spectra, this doesn't cause any problems. You just simply need to be careful. So we don't really need to know why. We just need to be just aware that happens, and that it happens in different ways. If you want to, you can go and just figure that out on your own. So what causes some frequencies to be absorbed? Each frequency of light, okay, including infrared, because infrared falls under sorry, we're just using example of light. It has a certain energy because it has a certain frequency, because waves carry energy. Now if the particular frequency being absorbed as it passes through it gets investigated, it must mean that if a particular frequencies are being absorbed as it passes through the compound being investigated, it must mean that the energy is being transferred to the compound. So if we have a compound, okay, and we're investigating this compound by shooting an infrared at it, and we see that this infrared wave with this specific amount of energy gets absorbed in it, that means the energy is being transferred into it, right? So we have energy like in the form of kinetic energy. Suppose when we put infrared, that means the energy from the infrared is going into it. So something's going to be changing within the things. Whether it's going to be the particles itself, whether it's going to be the bonds between the particles, something's going to be changing inside. Energies in infrared correspond to the energies involved in bond vibrations. This is going to be our main fact. Okay, your energies that you're coming from infrared radiation is going to correspond with the energies involved in bond vibrations. So when you have your bonds between the atoms of your organic element, or even just any element that you're shooting it into, that's going to be having bonds, and now that we're shooting energy into it, that's going to start vibrating. So it corresponds to that. Okay, that's all we're going to have time for today.